Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 1644, Lowest Common Ancestor of a Binary Tree 2. Let's read the question prompt. Given the root of a binary tree, return the lowest common ancestor, LCA, of two nodes P and Q. Either node P or Q does not exist in the tree, return null. All values of the nodes in the tree are unique. According to the definition of an LCA on Wikipedia, the lowest common ancestor of two nodes P and Q in the binary tree T is the lowest node that has both P and Q as descendants, where we allow a node to be a descendant of itself. A descendant of a node X is a node Y that is on the path from node X to some leaf node. Okay, so we've read the question prompt, and we need to make note of one important detail, that either node P or Q may not exist in this tree. Whereas in lowest common ancestor of a binary tree, 1, we were guaranteed to have P and Q in our tree, so it did make our solution a little bit easier. This question is a bit harder because we do have to account for the fact that nodes may not exist. Let's look at some examples. So we have this tree here, and we're told that P equals 5 and Q equals 1. So 5 and 1, we can see that the lowest common ancestor is going to be this 3, right? Because this is the first point where they converge when going up the tree. So that's how we get 3. What about if P equals 5 and Q equals 4? So it's this node and this node. So as we can see, it's going to be 5 because this is the first point where they converge. And remember that a node is allowed to be a descendant of itself. So that's why 5 would be the LCA here, because it's going to be the lowest common ancestor for this 4, and it's an LCA of itself. So this is the first point where they converge. Now let's look at the interesting case of P equals 5 and Q equals 10. So we have this node 5, but we can see in our tree that there's actually no 10 in the tree. And oops, I made a mistake here. This should not be to return 10. We should just be returning none here. Because actually, 10 is not in the tree. So therefore, we return null in the case when one of the nodes is not in the tree. So, there's two ways to solve this problem. And the first way is going to be the naive solution, which is going to be that you're going to traverse the tree, to make sure that both nodes are in the tree. So basically, you want to traverse the tree, make sure that P is there and Q is there. If either one of them doesn't exist, you can return none. If they both exist, then you could use the algorithm that you used in lowest common ancestor of a binary tree. The first problem, now that you know that they both exist, you can use, the standard LCA. But obviously that's not efficient. You're going to have to do one traversal of the tree to figure out if P is in there. You're going to have to do one traversal to figure out if Q is in there. Actually, you could just do it in one traversal. You could just level traverse everything. So maybe ignore that part. So you'd have to do one full traversal to check whether or not P and Q exist. And then you would have to do the second traversal to actually find the LCA. There should be a better way to do this, that we can only do it in one iteration. And let's look at that solution now. Okay. So we went over the problem introduction, we read the question prompt, and we talked about what the naive solution to this problem would be. But I did mention that there is a more optimal solution where we don't have to traverse the tree twice. We only have to do it one time. So let's think about how we might do that. The problem here is, again, that we're not guaranteed that P and Q exists in the tree. And we know that we have to return null if P or Q doesn't exist, or they both don't exist. So what this means is that we have to do a full tree traversal to figure out whether or not P and Q are in the tree. Because if they're not, then we know that, there's no answer for us to return. So if you remember from the solution of how to do LCA of a binary tree 1, for example, if we were working with the example of like 5 and 4 again, the second we saw one node that was actually equal to either, P, which would be this 5, or the Q, then we wouldn't even bother looking into the rest of the tree because we could just return, and then we would either find the LCA on the other side, or it would have to be, in 5 subtree, and therefore we could just return the 5. The reason we can't do that in this case is that we have to know for sure that 4 exists in the tree. Whereas in, the first iteration of this problem, you were guaranteed that, P and Q existed So we could return here without, any fear of not actually finding the Q. The problem with this problem, like I said, is that, P or Q may not exist. So we want to use basically the same algorithm as we did before, where, if we find a node that equals P or Q, we want to, return that node to its parent, but we can't do that before processing the rest of the tree. So, in LCA1, we could cut our recursion at the point that we found either P or Q and then return that node to its parent. Now what we have to do is, okay, we have to traverse the rest of the tree to see if we can find, the other node. And what we need to do is we need to maintain two Boolean flags, and we need to say whether or not P was found, and we need to say whether Q was found. So if we ever find P, then we'll set this equal to true, and if we find Q, we'll set this equal to true, and the algorithm is going to proceed the same as it did for LCA1. So for example, we'd start at the root. Let me get rid of all this. We'd start at the root and we'd say, okay, does 3 equal P or Q? No, it doesn't. Okay, so now we need to explore its left and right trees. So we go to the left first. So now we're at the 5, and we're going to say, okay, so we'll pretend that P equals 5 and Q equals 4, right? So we'll say, okay, we need to check, we need to find P or Q in the tree. So we can't just stop here because, this node equals to the 5. So what we're going to do is we're going to then explore its left and right children before we make any sort of processing on this 5. So we're going to go to the 6. Okay, does this equal P or Q? No, it doesn't. We go to its children, but they don't exist. So we end up back at the 6. Now we can actually process the 6 because we've done both of its children. And we can say, okay, does 6 equal P or Q? No. So this 6 is going to return a none to the 5, right? Then we go into, the right subtree of 5, and we're going to be at this 2. And then we still realize that, we need to process its children first. So, we're going to do this in a post-order manner. So we're going to process, the children first. We're going to go to the 7. Okay, is 7 equal to, actually, we do the check later, sorry. So we'll say 7. Okay, this is not null. So we go into its children. We see that they're both null. So now we can process the 7. So at the 7, we'll see, okay, is it equal to 5 or 4? No, it's not. So this 7 will return a none. Similar to how we would have done in the, LCA1. Then, okay, we go into 2's right child, which is the 4. And since it's non-null, we try to go into its left and right, which are null. So now we can process the 4 because we processed the children. So we'll see that, okay, 4 equals to Q. So that way we would set, Q found, our Boolean flag, equals to true, right? And then this node, instead of returning null, we can now return the node 4 to our, parent here, the 2. So now 2 is going to receive none and 4 from its children. And, 2 doesn't equal to 5 or 4. So what we want to do is simply return, the non-null one. So we would return 4. So this would return 4, and we'd be back at the 5. So now we can process the 5. The first thing we want to do is check whether or not this node 5 equals to P or Q. So we see that it equals to P, so we can simply say, okay, so we found the P now. So we say P found equals to true, right? So now we've processed that, and we received a none here, and we received a 4 from this side. But since this node actually equals to P, what we can do is simply return 5 here. It doesn't matter whether we return 5 or 4. It wouldn't really matter. And now we go into, the right subtree of 3, because we've now processed the entirety of the left. So we go to the 1. We see that, it's non-null, so we go to its left. We see, okay, we're at the 0. We try to go to its left, doesn't exist. Its right doesn't exist. And then what we're going to do is we're going to check, okay, does the 0 equal to P or Q? No, it doesn't. So that way we're going to return null here, or none. And then we go into the right subtree. We go to 8. We go to its left, its right. They're both null. So that means that we, we check, okay, does 8 equal to P or Q? No, it doesn't. So that way we're going to return none here. And then we're at the 1. Okay, now we can process, does 1 equal to P or Q? No, it doesn't. And then we just return, left or right in this case, because it doesn't equal to P or Q, and neither of the children were defined. They're both none, so we return none to the 3 here. So 3 is now receiving a 5 from its left subtree and a none from its right subtree. Now we check, okay, does 3 equal to P or does 3 equal to Q? No, it doesn't. And now what we return kind of like globally is, we would return 5 from our function. So we would return a non-null node from our like recursive, I guess, DFS function that we would write here. And the last thing we need to do is actually, for our answer, if the function that did this entire DFS returned a non-null node, which it did, okay, so that means that we found a potential LCA if and only if both Q found and P found are true. So we're allowed to return our LCA here, which would be the node 5, if and only if Q found equals T. So for example, our return statement would be, return true if, DFS of, on the root node, and Q found and P found, else we have to return false. So we have to find Q and, P, otherwise we can't return true. Because for example, if you remember, when we had the case where, P was 5, but Q, oops, what am I doing? Q was actually 10, our function here, if we ran this, would still return 5 here, because, we did find a node 5, but, since we never found 10 because it doesn't exist in the tree, we could be lured into saying, oh, actually we found an LCA, but in reality, since we didn't find the Q, even though our function, this DFS, is still going to return this 5 here, the fact that we didn't find Q means that we have to return false. Otherwise, our solution would be wrong, because as you can see, there is no 10 in this tree. So that's why we have to make sure that Q is found and P is found, to make sure that if our DFS function returns, a non-null node, then we can return true. Otherwise, we have to return false, because obviously if one of the nodes doesn't exist, then it's false. So that might be a little bit confusing. Let's go into the editor and we'll write the code, and it should be relatively straightforward. Like I said, this is going to be a post-order traversal, where again, we want to check the children of a node before checking the parent here, and then returning up back to the parent. So I'll see you in the editor. Let's write the code and let's figure out how to do this problem. Okay, we went over how to conceptually solve this problem in the most efficient manner, but how do we actually write the code? So let's implement it. Remember that we need to make sure that P and Q exist in our tree. So let's define 2 Boolean flags to keep track of this. So we're going to say self.pFound is going to be equal to false because we haven't found it yet. Self.qFound is also going to be equal to false because we haven't found it yet. Okay, now remember that we want to see if our DFS function will return a non-null node, because that indicates that we found at least one of the nodes in the tree. We're not guaranteed that the node we found will be the LCA, but if it doesn't return anything, then that means that neither of them are going to be in the tree. So we need to at least have some result here from our DFS. So we're going to say, answer is going to be DFS, and we'll define DFS in a second. So we'll say DFS, and we're going to call this on the, the root node that we're provided. And remember, our answer was only the answer if Q was found and P was found, because that would indicate that it's an LCA. So let's say, okay, return ands if Q found, let's see, if Q found and, let's see, P found, else none. Right, because we're returning a tree node here, so we want to return none instead of false. So let's define the DFS function. So we'll say def DFS, and we will just take in, a node, right? Cool. So how do we write this function? Remember that, we were doing this in a post-order manner, and obviously one of the things we have to do is make sure that the node that we're processing is actually, non-null. Otherwise, there's nothing we can do. If we've hit, the end of the tree, where we've gone to, null left and right subtrees, then we can't do anything. So we have to make sure that our node is actually processable, aka not null, before we can actually do anything on it. So let's check that. We'll say if node, if not node, then we just want to return none, because there's nothing we can do here, right? There's no LCA that we can find. Otherwise, we need to do the processing. And remember that we're doing this in a post order manner, so we want to process the left and the right subtrees before we process, the actual node itself. So we're going to say left is going to be equal to self.dfs of node.left, and we're going to say right is going to be equal to self.dfs node.right. So that's going to be us processing the left and the right subtree. Now, when both of these recursions finish, what we want to do is then process the node that we're at, because again, this is a post-order traversal. So now we can do the check of whether our current node equals to P or our current node equals to Q, similar to how we did in, LCA of a binary tree 1. So we're going to say if node equals to P or node equals to Q, that means that one of, this node is either, P or Q. So we need to check which one it is actually. So we're going to say if node equals to P, we're going to say, self.pFound equals to true. Otherwise, that means that we found Q, and we're going to say self.qFound equals to true. Right? And then at this point, we can actually return the node, because we know that this is our potential candidate for an LCA. So we can return the node. Otherwise, if the current node doesn't equal either P or Q, what we want to do is, actually we can just get rid of the else here. We can say, if it doesn't equal to either P or Q, but, we were able to find P and Q in its left and right subtree, which we'll get from this L and R here. If we receive non-negative, non-null nodes from, these recursions into the left and right subtree, and that would mean if both L and R are non-null, then that means that our current node is the actual LCA. So we're going to say if L and R, so if both of them return non-null nodes, then we can return our node, because we know our node is actually the LCA. In this case, it was where, since a node is allowed to be the LCA of itself, that's why if it equals to either P or Q, we return the node here. This is like the more formal definition of an LCA, where, the nodes are in its subtree, and this is the first point where they converge. So if that's the case, then we can return null. Otherwise, not the node, sorry, not null. Otherwise, we would just return L or R. Return L or R. And that's what we want to do. Okay, so we've written our DFS function, and now let's submit it and make sure that this works. So, this should be actually self.qfound. Fix some bugs before we run this. Self.qfound. Okay, pfound, let's double check. Okay, this should work. And P. I forgot to pass in P and Q here. Apologies for that. Let's see, node PQ. God damn it. Okay, node PQ, and then we want to call this PQ. Okay, cool. If we pass these in now, this should. What is going on? Okay. God. Whoops. Bad radio here. Okay. And there we go. Okay. After a few stupid bugs, we basically fixed our solution. So we can see that it works. Like I said, this is going to be, an optimal solution because we're only doing one pass to the tree. Time and space complexity wise, let's think about this. So we know that we have to traverse the entire tree to find whether or not P or Q is found, which means that because we're traversing the entire tree, this is going to be a big O of N solution, right? We have to touch every single node in the tree to make sure that P is found or Q is found. And we don't stop our recursion early if we find either P or Q. We do explore the entirety of the tree, so that's why our time complexity is going to be big O of N. Space complexity. Okay, this one is a little bit trickier. If you want to count the stack frames from the recursion, it's going to be a big O of N solution because you have to traverse the entire tree, and in the case that you had a very skewed tree where it was just like all left subtrees, it would be big O of N. But if you don't want to count this, so we'll say big O of n if counting stack frames, otherwise it's going to be a constant space solution, because obviously the only variables that we define here is going to be these two Boolean flags, but this is a constant space allocation. So there's no, extra data structures used here. So, you can bring this up to your interviewer. You can tell them, okay, if we want to count the stack frames, it's going to be big O of n. Otherwise, it's going to be a constant time algorithm. This is generally good enough for most interviewers. They say, okay, the guy's thinking about the fact that, you're using recursion here. That's not like technically free. So you should get a pass on this. But this is going to be your time and space complexity. I hope you enjoyed this video. If you did, please leave a like, comment, subscribe. Tell me what other videos you'd like to see. I'm happy to make whatever video you want. Hopefully it's not some crazy obscure question that nobody knows the solution to, but I'll do my best to figure it out, make a video, explain it for you guys. Anything you guys want, please just leave it in the comments. I'll do my best to get back to you and make those videos. Otherwise, happy Leetcoding.